Hi everybody, today we're going to be talking about the history of the atomic model. This video will consist of two parts. The first is a timeline of scientists and their contributions, and the second part we will look deeper into the atomic models. So here we have a timeline of important scientists and their significant contributions to our modern atomic theory. We go all the way back to 5th century BCE. Democritus and Leucippus, they believed the world was made up of atoms, and Democritus also coined the term atomus, which means indivisible. 1 century later, in 4th century BCE, Aristotle came along and he thought differently than Democritus. Instead of believing that the world was just made of atoms, he believed that the world was made of four basic parts: water, fire, air, and earth. Then we flash forward all the way to 19th century AD. John Dalton thought back to Democritus' ideas and created Dalton's atomic theory, which we'll look at a little later. Next, we have Goldstein, and he experimented with the cathode ray tube, and although he didn't have any significant contribution directly, his work helped future scientists with the discovery of subatomic particles. And next, we have J.J. Thomson, and Thomson conducted an experiment with the cathode ray tube. This yielded the discovery of an electron, and he also created the plum pudding model after his discovery of the electron. Then we have Max Planck, and using quantum physics, he created the quantum theory. Then we have Nagoka creating the Saturnian model, in which electrons orbited in one shell around the nucleus. Next, we have Robert Millikan, who conducted the oil drop experiment to yield the size of the charge of an electron. Ernest Rutherford conducted the gold foil experiment, and his findings are shown in the nuclear model of the atom. Niels Bohr came next, and he, using spectroscopy, created the Bohr model. And Erwin Schrödinger used mathematics to approximate the location of electrons. He created the electron cloud model. And these scientists we will look at later in the video in more detail. And lastly, we have James Chadwick. Chadwick is accredited with the discovery of the neutron. In this next part of the video, we are going to look at 6 important scientists and their significant contributions to our understanding of the atom. So first we have Democritus, and like I said before, he lived back in BC. And he conducted an experiment in which he took a seashell and he broke the seashell down until it could not be broken down anymore. And this gave him the idea of a basic fundamental particle that is a component of all things. So using this logic, he coined the term atomus, which means unbreakable or indivisible. Next, we have John Dalton, and like I mentioned earlier in the timeline part of the video, he was an Englishman who lived from 1766 to 1844. And he was an extremely smart man. He was a school teacher by the age of 12 and was extremely interested in meteorology. In fact, he collected air samples from all over Europe and really wondered about the composition of air, which is what led to his atomic theory. So instead of conducting experimentation on his own, he used Democritus' idea of an atom, Proust's law of definite proportions, and Lavoisier's law of conservation of mass to create the billiard ball model, which, as you can see here, is just a solid, indivisible sphere. And notice how there are no subatomic particles. There are no protons, electrons, neutrons, there's no nucleus. He just thought it was an indivisible sphere. And to back up his statements, he created Dalton's atomic theory, which we're going to look at here. So Dalton's atomic theory is 5 postulates. The first says that all elements are made of tiny particles called atoms. Second says atoms of a given element are identical in size, mass, and other properties, but atoms of different elements differ in size, mass, and other properties. He also says that atoms cannot be subdivided, created, or destroyed, and atoms of different elements can combine in simple whole number ratios to form chemical compounds. And in chemical reactions, atoms are combined, separated, or rearranged, and that's where the law of conservation of mass comes in. Dalton was not believed at first, but there were some changes to his atomic theory that took place in the early 1900s. First of all, as Dalton claimed before, it could not be subdivided, created, or destroyed, which later we found out that the atom was in fact divisible, not in ordinary chemical reactions, but in nuclear physics. He also claimed that atoms were identical in size, mass, and other properties. This is not exactly true because isotopes exist, which are elements that differ in the number of neutrons and therefore have a different mass. So we still use his model with some revisions today, and this leads us into our modern atomic theory, which includes changes to Dalton's atomic theory. Atoms of an element are nearly identical, but they may have different masses. Atoms are not indivisible, but they are composed of subatomic particles. And matter is neither created nor destroyed in ordinary chemical reactions. Next, we're going to take a look at J.J. Thomson. J.J. Thomson conducted his famous experiments in 1897. He experimented with the cathode ray tube, and he had 4 major observations and hypotheses, which we are going to go through. His first observation was that ray properties are independent of the cathode material, and this led to the hypothesis that cathode ray stuff is a component of all materials. He then noticed that cathode rays bend near magnets, and the hypothesis from this was that magnets bend the paths of moving charged particles. Maybe cathode rays are streams of moving charged particles. His next observation was that rays bend towards positively charged plates. Rays impart a negative charge to objects they strike. And his hypothesis from this was that cathode rays are streams of negative charges. Next, he realized that cathode rays don't bend near small obstacles, they do not cast sharp shadows, and they can turn paddle wheels placed in their path and can travel in straight lines. So his hypothesis from this was that cathodes behave like streams of particles. Subatomic particles mean smaller than atoms. And what does all that mean? That basically means that cathode rays are negatively charged subatomic particles, which we call electrons. And from this, he created the plum pudding model. The plum pudding model is a sphere of positive charge. The pudding in the background is positive charge. Then we have some plums in the middle that are just negative charges or electrons floating around. Next, we have Ernest Rutherford, and Rutherford conducted the gold foil experiment. The gold foil experiment fired massive alpha particles at atoms in thin metal foil. And he decided to use gold because it, first of all, could be cut into very thin foil, and also it's highly metallic. So if Thomson was correct, he would expect particles to just run straight through the particles, sort of like bullets. He discovered that although some particles went through, showing most of the atom's volume is empty space, few particles unexpectedly ricocheted, showing that there was a small, dense, positively charged nucleus. So he created the nuclear model, which had these proton-filled nucleus. It was a positive charge, and all around it he had electrons orbiting the nucleus. And he had these going in one specific pattern around the nucleus. Next we have Bohr, and he conducted an experiment through the use of spectroscopy. Basically, he looked through a spectroscope and noticed that light energy was radiated in discrete states, not continuous. So he would have seen something sort of like this. This is the background of the spectroscope, and he would have seen a red line here, and maybe an orange line here, and then a yellow line here, a green line there. And this showed him that electrons must orbit in specific allowed orbitals. And this failed to account for certain chemical properties and could not explain the Zeeman effect, but overall it was a very informative model. So it showed a dense positively charged nucleus here. Then it had orbitals all around in which electrons orbited the nucleus. And it's also important for you to know that within the first ring, there were 2 electrons. In the second ring, there were 8 electrons. The third ring, 18 electrons. And the fourth ring, 32 electrons. Our last scientist is Erwin Schrödinger. He used mathematics to predict the location of an electron. And first he claimed that it was impossible to know the exact location of an electron in orbit. So his model focused on the trajectory of an electron. It's called the electron cloud model. So what it looks like is a dense proton-filled nucleus in the middle, and all the way around it we have a cloud, and this cloud is filled with the possibility of where an electron could be found. And you'll notice that closer to the center, the cloud is darker. Next, we have a summary of what we covered in the video. Democritus used the Cecil experiment to lead to the idea of an atom. Dalton used previous findings to explain the atom using the billiard ball model. J.J. Thomson used the cathode ray tube to discover the electron and create the plum pudding model. Ernest Rutherford used the gold foil experiment to explain dynamics of the atom, and he created the nuclear model. Niels Bohr used spectroscopy to discover orbitals and create the Bohr model, and Erwin Schrödinger used mathematics to predict the approximate location of an electron in orbit and create the electron cloud model. Thank you for watching.